Hello, everyone. So, we will be talking about mobility, isotopes, and archaeology. And this lecture is in continuation of the last lecture, which was also on isotopes and dating. But this time, we'll be looking at a very different approach of isotopes and archaeology, and that is mobility. Okay, so if you did attend the last talk, you would remember this diagram very well. Uh, Pretty concise diagram which tells us about isotopes and their implications. So there's diet, there is climate, there is dating obviously involved. But if you can look at this part of the picture, it talks about provenance or mobility using strontium. And this is what we'll be focusing on our lecture today. So when we talk about isotopes, for the sake of mobility, a number of isotopes can be analyzed. But to make the talk more coherent, to make it more easier to understand, we will be focusing only on strontium today because strontium has a lot of potential to offer in archaeology and some very interesting case studies that will help us understand how this entire procedure works and how it can be applied. So, just a basic layover of the talk. We'll be talking about strontium isotope, how it is used in archaeology, the basic principles involved, the theoretical considerations, how the samples are taken in, and how it is applied. And then we will not just end the lecture on seeing the potential of strontium, but also understand that it is important to be critical while using strontium or any sort of isotope. So let's begin. Now, this is a picture of the strontium crystal. Uh, what strontium exactly is? Strontium is an isotope and it is a naturally occurring isotope. Strontium is an element which has four naturally occurring isotopes: strontium 84, 86, 87, and 88. Strontium 87 is radiogenic, which, if you remember, means that it will decay, while the other three will not decay. So you have three isotopes which do not decay and one isotope which will decay. The half-life of strontium 87, as you can see, is 4.88 into 10 to the power 10, which is a fairly large temporal span. And by this, like unlike carbon 14, which had like just 5,730 years, this has a very long range. And therefore, strontium is not usually used for dating of artifacts, but it is used for other purposes because of its fairly consistent decay rate, and that is mobility. Strontium in itself is a trace element which is found in all sorts of rocks. So whether it is an igneous rock, a metamorphic, or a sedimentary rock, you would find strontium in different ratios present in these naturally occurring geological profiles. Um, then, through weathering and other human as well as natural factors, strontium will erode and it will enter water bodies like river, groundwater, seawater. It will enter into soil. And when this soil would bear plants, plants will be extracting nutrients from the soil, and strontium would then get onto the plants. Plants will be like it will be absorbed by the plants. It will be eaten by the animals, by humans. Humans will eat animals. So the entire trophic level would move ahead, and so would the strontium concentration as well. So if you just think about this for a while, strontium is actually present in almost inorganic as well as organic substances. So it's there in the rocks, it's also there in water bodies, it's there in plants, it's there in human bodies, it's there in our bodies as well. And this is how widespread strontium uses. It's a trace element, always remember it. It's not present in huge quantities, but it's present still. So the basic principle involved here is that since we know strontium 87 is a radiogenic isotope, and strontium 86 is a stable isotope, and therefore it's even in number. So the ratio here of strontium 87 and strontium 86 is measured in different kinds of rocks. So let's say there are like igneous rocks, usually formed of volcanic activities, sedimentary rocks eroded and then deposited over the years, and metamorphic rocks, when rocks undergo crystallization, other processes, have different ages, right? And if they have different ages, they will have different levels of strontium 87 and strontium 86 ratios. This is what is measured in strontium isotope analysis. The different ratio of strontium 87 and strontium 86 can tell us about how old or young a given rock sample is, how old or young the geology of a place is, and how does it help in archaeology? We'll see. Okay, this map, or the map that you did see in the beginning, a very colorful map, it's an isoscape. I'll just talk a bit about what an isoscape is. So these isotope ratios, as I said, that there are different rocks, like the Earth's crust is formed of different rocks, and these rocks have different levels of strontium ratios. We are talking about strontium, therefore strontium ratios are different in these rocks, and different ages when they were formed. So when we map this difference in isotopes, we call that an isoscape. So you can see that there are different levels of strontium 87 and strontium 86 that have been marked, which can tell us that the geology here is fairly older, fairly, this one is fairly more recent, and this entire isoscape is usually made for understanding the isotope distributions, to understand the age of rocks, and it is crucial for any sort of analysis of isotopes that are found on Earth. So strontium is there. There are also lead isoscapes that are formed. There are oxygen isoscapes that are formed. So every isotope that exists on the surface of the Earth, it can have its isoscape mapped. And this is very, very important in case of any sort of analysis um, of isotopes in archaeology, talking about mobility. Now, you have the isoscape map. So I know the 87-86 ratio of different regions. And my sample here is, my archaeological sample here is a bone. I find it. And then I will analyze the 87-86 ratio in that bone. And I'll compare it with the geological strontium that I found from the rocks. And then I can match the two and see if the bone has almost the same level of the 87-86 ratio as the lithology as. And if it's the same, that means the bone would have been extracted from that region. The organism would have lived in that region. They would have consumed plants and water from that area, and therefore the strontium concentration in the body of that organism is similar to the naturally occurring geological strontium in that region. That is the basic principle of identifying provenance and movement in strontium. So just remember this thing, like if you are in like in case of India, the strontium levels will be different from for northern India and for southern India. The 87-86 ratio will be different. If I have lived my entire life in northern India, then my 87-86 ratio in my bones will be different from the 87-86 naturally occurring ratio of rocks in, let's say, the Deccan region. And therefore, you can say that if you find my bones and not anything else, that this person would not have lived in southern India, but 87-86 ratio is fairly closer to the one found in the northern plains in the alluvial basin, and therefore my provenance will be traced in the northern region. Now, use this case study in case of bones found thousands of years earlier, where you have no written records, where you have no written sources. But think about it, you can actually identify where a person would have come from or would not have come from. This is important because this is also, while this is the potential of strontium analysis, this is also a limitation of strontium, but we'll come to that later. But understand this, that you have nothing available, but still strontium isotopes, and therefore you can use them to trace movement. And it's even important in case of strontium because the human anatomy further supports a series of understanding different strontium compositions if a person traveled through different regions. I will not complicate it further here. Here, I will just end it with the basic principle, and let's consider some important things here as well while we're talking about this fairly simple comparing part. So, um, if you remember the last talk, you would remember the process of fractionation that occurs in isotopes. So, strontium analysis relies on this principle as well, that there is little or no change in the strontium levels or the isotope levels of the rocks present from whenever they were formed till present day, which is not really true because landscapes change, erosions take place, natural or human factors, both of them are responsible. But then this is again a consideration that has to be taken in mind. The another thing is that in a given rock, strontium is not the only element that is present. There are a number of other elements present in those rocks, and they would react amongst themselves as well. So, the very idea of how metamorphic rocks are formed. Metamorphic rocks are formed because of chemical processes that take place within a rock. And if that is happening, that means that the elements would be fusing with one another, and it might also hamper the strontium profile. The third thing here is to understand the inputs and outputs during weathering. Now, if you see a rock that is formed maybe in the Himalayan region, and because of river activities, because of the erosion of the rock, the sediments would be brought down and the sediments will be deposited gradually in the northern plain region. So, what happens here is that the original sediments that were from the Himalayan region, they have the strontium profile of the rocks present there, but they are being deposited in the northern region. So the strontium ratio will be different in case of northern region and the upper Himalayan region because of the fluvial activity. This would be fairly similar, which will create problems in creating an isotope. So there are inputs and outputs. Input, like here, the deposition of rock, and output here, the weathering of the sediments from the uppermost regions. So isotope mixings do, do also take place, and this can be a possible, at least in theory, it is believed to be a possible contamination because of natural factors which can occur and which would lead to problems in analysis. But but here is the silver lining. Researchers like Britain and Slovak and Payton, who have done work on strontium isotopes, they have said that these processes can be averaged from the weathering of rocks to the entire trophic level concentration of strontium from different, like from plants to animals to the human body, or from if the organism is consuming um, marine organisms. Even in those cases, this can be averaged out. Further, in lab analysis by using of spectrometers and other instruments, that if there are differences in the strontium composition of the original geology and the secondary geology, this can still be equated. So the conclusion from this slide is that the theory that we had discussed earlier, it remains the same. So strontium ratio difference in rocks and the strontium ratio difference in case of human body, if that is sample, is compared and the provenance is identified. Jonathan E. Erickson was the pioneering archaeologist who actually utilized strontium for mobility. He was a part of University of California, and he tried to understand seasonal and non-seasonal migration amongst a Native American tribe, which is found on the southern coast of California. In his study, he did not really create any isoscape. He took the burials, the skeletons that were found. He calculated the strontium 87 to 86 ratio amongst them, and he found that the ratios were different for different burials, which means that they could have consumed a different diet because strontium enters human body through diet. So they could have consumed different diet, but they were not really sure if that is because of changes in diet. So were they consuming C3 plants or C4 plants, or it was because of movement. So they utilize both the carbon isotope analysis and strontium analysis to understand that was it mobility or was it the diet. In this study, no isoscape was created, but we have to understand that this was the first application of strontium, and so this is where the beginning of strontium took place in archaeology, and it has been almost 4 decades. And strontium has been utilized in a number of case studies in archaeology that we will be discussing in this lecture. So, the next part here is going to be understanding how the samples are taken in for strontium studies and how it is taken for different sort of laboratory analysis, because it is important to understand this, as different instruments can give different readings. And this I'll go through quickly, but please be a little more attentive here, because any problem in sampling would lead to potential problems in analysis and therefore in interpretation. So, in case of humans and animals, we know that calcium is what is essential for our bones, but calcium is replaced by strontium. And so, the inorganic part of the bone, so there's an organic part from where you extract DNA and carbon, other things, but there's an inorganic part which is called bioapatite, and bone, tooth enamel, and tooth dentine are the ones which are used for extracting strontium from human body. Enamel is the outermost part, the hard part of our teeth, and then there is dentine. Enamel is considered to be one of the ideal samples for human bodies to extract that strontium 87 and 86 ratio, and it is formed usually during childhood. But this is considered more ideal than dentine because it is less susceptible to any sort of contamination or diagenesis. Diagenesis is a sort of contamination that takes place after an organism dies. So researchers try to look for enamel usually, and I would really take a few minutes because this is very interesting to understand. Now, we all know that the 32 teeth we have in our human jaw are made, and then they fall off, and then the other set of teeth appear. And so the teeth of a human body show different phases of a human's life, which means they also show a different show differences in phases of strontium consumption of a human body in different phases of its life. So, your first molar, second molar, and third molar, if I extract it from a skeleton, let's say, the first molar will tell us about the diet of an organism, diet like from where the person was consuming food for the first 3 years of their life. Then for the second molar, it tells us about where they would have lived in from from 3 to the 7 years of their life, and the third molar can tell us about 9 to 12 years of where they spent their life. So the differences in the ages of the formation of the teeth tell us about the differences in where a person would have lived in their life. So again, just a hypothetical example. If I was, let's say, born in northern India, um, currently I'm in Italy. So what happens in this case is that in the early phases of my life, because I have stayed almost all my life till now in northern India, the my teeth will be reflecting the geology of my region, because I have been eating food here, I've been drinking water here. So the strontium present here is from the strontium of the rocks present in my region, and that is what will be shown in case of my analysis, geology of my region. However, in case of bones, this is a bit different. Bones form throughout the age an organism lives. So the strontium isotope present in the bones is of the later age of a person's life. So let's say currently I'm in Italy, and I'll be staying here for at least 2 years or maybe more. And so the food that I'll be consuming here will be grown in Italy. And so the strontium that is entering in my body right now is from the rocks and the nutrient profile of soil present in Italian region. And so my teeth and my bones will have very different level of strontium isotope ratios, which can help us understand movement. Now, in case of bones, bones are more prone to contamination. This has to be understood and kept in mind. However, when we are talking talking about bones, we usually talk about the petrous bone. So, petrous bone is part of the temporal part of our skull, and this red region, if you see the inner side of it, that's where the petrous bone is located. It is the densest bone in human body, and even if the body is burnt, so even if the body is cremated, the petrous bone will still survive intact. And so in 2015, DNA researchers, when they found out that petrous bone still survives cremation and can be used to extract organic material, it was also realized that it can be used to extract inorganic material. And so, if a body is if a body is found and the petrous bone is intact, it is usually located by researchers for understanding or for gaining strontium for that person's for that individual's strontium profile. Now, uh, while I did talk about sampling, another thing to be borne in mind here is that as an archaeologist, if we are dealing with strontium analysis or any sort of isotope analysis and we are sampling human body, we have to understand how much we can sample from that body, from a given skeleton. It's not like you can take all the bones. It's not like you can take all the teeth and you can just extract the strontium isotope ratios present in them. It is nothing else but destruction. And archaeology, although we all are studying or are going to study archaeology, is often considered as a science of destruction. So you have to be very, very careful while extracting samples and knowing which sample you're extracting and for which purpose. You can extract n number of teeth, but do understand that will create tension in the skull, in the jaw, and it's a skeleton. It has died years ago. That means it is already in a very fragile state. If you are trying to extract the petrous bone, remember it's on the inner side of the skull. If you are doing this, you will damage the skull as well. So, as researchers, it is important to analyze that this is important to understand that you cannot just go on extracting everything or sampling everything because you want to study or you want to conduct any sort of isotope analysis. It will have its repercussions. And so, what the objective of our study is has to be understood first before delving into getting the samples, because that cannot be undone. So, yes, okay, finally we come here. If we extract samples of within skeleton from the teeth, from the enamel, and from the bone, and we compare the isotope ratios. So, if the isotope ratios, see, the teeth are formulated when you are young, when you are a child, and the bones are formulated when you are an adult. So, if the strontium ratio of 87, 86 is the same, that means the person would have the first interpretation is going to be that the person has stayed in that region throughout their lives. The second interpretation might be that they would have moved to another locality but might be consuming food from their original provenance, which can happen in a number of cases, considering that exogamy, when it is practiced or when a woman marries into a family quite different from their origin from her original clan, she might be relying on diet from her original or native family, and so she might be consuming food from her native family, and therefore there might not be much difference in the enamel and the bone isotope ratios, and that could also suggest the same, that no migration might have occurred, although it might have. So but yes, the first consideration is going to be that the individual was born and it lived in that area throughout their lifetime. Another consideration could be that the strontium ratios would have been fairly similar in both the places. So let's take another example. Uh, I'll just give examples of from that I taken when I tried to study this. So I was born in Allahabad, but I stayed in Delhi, and maybe if I stay in Delhi for the rest of my life, there is not much difference in the rock or the geological profile of Delhi and Allahabad, and so the enamel and the bone ratio of Allahabad, of sorry, of my skeleton would be fairly like same. Why is this? Because the strontium profile of both the regions is more or less same. It would not be the same in case of Italy, but it would be same in case of these two places, which will be difficult to identify any sort of movement taking from one region to another. The other, the other outcome could be that the ratio is not the same. which suggests mobility or movement, because the person would have been born in one region, they would have consumed food in that region till they were a child, and then they moved to another region. And in the later phases, because the strontium ratio is different in case of bones, it would suggest that they moved to another region, um, and therefore there's movement that has occurred, and that is the interpretation from this difference in isotope analysis. Now, another possibility could also be there, but I think so. We will study this more with the case studies than delving into it right now. Um, the next part, okay, I just thought this is something important to also discuss here. How does a spectrometer work? So, for understanding any sort of isotope or to understand any elements, a sample, like if I give you tooth, a tooth, and you have to understand the isotope ratio present in that, you will be putting it into a spectrometer. After treating it, after removing all sort of physical and chemical contamination, you will be putting it into a spectrometer. And if you put it in there, how does a spectrometer actually help us in understanding isotopes? So I'll just go very quickly through this. Um, you take in your sample and then you heat it up. And when you heat it up, what happens? The ions will be charged in that isotope. Remember, strontium or any sort of isotope analysis, it's a destructive practice. The sample does not survive in most of the cases. We discussed this in case of carbon dating as well. It's the same with strontium. So the ion will be charged. So although a very less quantity of sample is required, but still the sample would not survive. The ions are charged, and when the ions are charged, now isotopes have different number of neutrons in their nucleus. So what would that mean? That one isotope would be heavier, the other one would be lighter. And if there is a difference in their weight, there'll be difference in their movement, which takes place after they have been charged. And since there'll be a difference in their weight, they'll be put into an magnetic field, which will cause deflection in their movement. And since there will be a deflection seen, the heavier isotopes will not deflect more because they are heavy. They cannot change their direction so easily. But the lighter isotopes, they'll be easier to like deflect. And if they deflect, they would be falling onto a detector, as you can see here. And when they would fall on the detector, they would create a spectrum. So the spectrometry works in this mechanism, that the differences seen in the falling of the particles is then analyzed through various laboratory methods, and the isotope is determined. So that's the working of a basic spectrometer, and how isotopes are analyzed. This is important because in isotope analysis, we usually rely on two of the known spectrometers. So one is TIMS, or thermal ionization mass spectrometry, which was used earlier. It is more precise. It requires less sample for understanding isotope ratios, but again, it is more expensive and a very time consuming equipment. The other one that is used nowadays is the MCICP-MS, which is multi-collector inductively coupled plasma mass spectrometry, which is more popular nowadays because it gives like you can analyze 4 samples in a day, which is fairly quick considering the time that has taken place in case of TIMS. However, it is a bit less precise and it requires more samples, but it is comparatively cheaper as well. So there are pros and cons of both the methods. And while we are reading papers on strontium or on any sort of archaeological analysis that are done on them, it is important to bear in mind which of these spectrometers have been used, because they'll be giving different results as well. It might not be a huge difference, but then in isotopes or any sort of laboratory analysis, even minute differences can have huge implications. We'll also study this when we see how an isoscape is created. So here we are done with the theoretical part, the sampling and everything, and now we can finally delve into the case studies of strontium and to see how much potential strontium holds for archaeologists. Now, This is one of the, I can say, a primary case study which helped understand a very important phenomena in European prehistory, which is the bell beaker period. Now, bell beaker, this is a bell beaker, by the way. This kind of pottery is called bell beaker, and bell beaker was a pottery culture that existed between the Neolithic and the Bronze Age of Europe, so around 2500 to 2000 BCE, and before any sort of DNA analysis, before any sort of isotope analysis, when archaeologists looked at the burials and the associated archaeology, that is all the burial goods, they said that, oh, these people are very different from the pre-existing Neolithic people that were there in Europe. So is there a possibility of migration? So migration or diffusion was suggested, but it was not verified by any other source. However, what Price and others did in their study, they took skeleton samples of 81 individuals, so from the bone and the teeth, and these samples were taken across from places in South Central Europe. And an isoscape was first of all created for the South Central Europe region, so you know your entire Eastern European region. And after that, an isoscape of that entire area was constructed, and then the samples of the 81 individuals, their 87 and 86 strontium ratios were laid down, and then they were compared. And from the analysis of the bone and the teeth sample, it was very clear that they were different, which means 51 individuals had very different strontium isotope ratios of their teeth when compared to their own bones. That means they were born in a different region, but they died in a different region. In this case, if it's South Central Europe, and so migration was attested for. This is one of the primary case studies because it helped us understand about the Proto-Indo-European expansion, which is now a fairly well understood and documented historical migration through both isotopes and through the DNA studies. But it showed us how isotopes, especially strontium, can be used to understand where a person is coming from and where a person would have died or would potentially have been born. Now, this is another case study that was done in Mexico. And what the researchers found here was that in this place called Campeche in Mexico, which is a colonial town. So in 17th century, what the researchers found was that there were burials, and the burial practice was very different from the burial practice seen in case of the Native American population. So there were decorations seen in the burials which were similar to the ones seen in Western Africa. But 17th century, they could not really understand that what exactly did this ascertain, because nothing else was written on the burials, nothing else could be understood from the associated archaeology. So they took isotope ratios of 10 of the burials, and when they used the isotopes, they found that they were very different. Five of them were very different from the Native American or from the geology of the region, which means these five individuals must have come from a different region. And so it was believed that they might have come from Africa, and this could be an interpretation pointing towards an early example of slave trade in Central America. So this case study actually showed that this could be an example of early slave trade. However, something very important here to be pointed out is that no conclusive evidence was held that yes, we know that the five people who have died here were not natives, but where did they actually come from? This was not something that could be understood. And this is one of the leading problems with strontium isotope analysis. They can tell you, if you take a burial, if you find a burial and you compare the local geology of strontium isotope with the isotope present in the human body, then yes, the person has not died here. They came from somewhere else. But where exactly they came from, this is something that is still not that easy to understand, or still cannot be stated just by comparing isoscapes. And this this has to be understood because this points to two further problems in strontium research. First of all, not every place has an isoscape being made. So the strontium isotope ratio for every region, especially in South Asia, has not been made. And therefore, if a burial, like if an Indian, let's say 5,000 years ago, living in India, would have died in Europe, you would not be able to tell that they came from India because the isoscape of this place has not been made. Even in case the isoscape would have been made, strontium isotope ratios are not that distant for every region. This I will show through another case study. So let's leave the critical part for the later part of this talk, and let's just move on to other case studies. Um, okay, this one, and again from Central America. Um, Trophy heads, which were seen in case of Vari Empire, which existed from 600 to 1000 CE. What they found were there were certain trophy heads that were displayed in graves, and the researchers wanted to understand where these trophy heads came from, or who were these people exactly. So these heads, as you can see, they showed violence. So there are holes dug in the skulls, which points out that they may have been subjected to some sort of violence before the people who have these skulls would have died. And so strontium isotope analysis of 5 of these heads was conducted, and what the researchers found was that they were not a part of the local tribe, they were not from the local region, which led them to believe that maybe these people could have been enemies, and they would have been captured during the war or defeated during the war, and as a means of exerting the authority of the Bari Empire or their victory over these enemies, they would have been subjected to this violence, and their heads would have been displayed as trophy heads. This was also something that they did parallel out with the associated archaeological pieces. Like in this case, it's a potsherd, and here, as if you could see, like this monster kind of a creature, it's holding 2 figures. So the prisoners of war were treated brutally. This has also been attested through the pottery and other analysis. And so researchers tried to understand this, that these people would have come from some other places, they might have been enemies, and so they would have been subjected to such atrocity. So if we keep the principle of strontium isotopes intact in our minds, so we know local strontium, geological strontium, and the strontium present in human body, if there's a difference, it will suggest movement. And this same principle has been applied in so many archaeological scenarios. So in this case, burials of females was analyzed from the Longshan period of Chinese history of 2500 years, 2500 BCE. And since the women showed a different strontium profile than the men, it suggested that that female exogamy might have existed in that period. Another one of the case studies, and this one comes from England, showed the same, and therefore it was subjected that during the 7th century CE, since the burials of the people were showed different strontium ratios from the local burial, that means that these people might have come from outside, and since it was in a large number, it could have subjected to colonization of England that may have taken place in around 7th century CE. Now, strontium is not just analyzed from the human body, it's not just sampled from human skeleton, it is also present in animals. And when we are talking about animals, pastoralism or any sort of nomadic activity can also be interpreted. So, what the researchers did in this case, this is a case study from Southern Africa, they found bones of sheep, cattle, eland, and steenbok animals, and they first of all, use the carbon and oxygen isotopes to determine the diet. So, was it the C3 diet or the C4 diet? So, the more C3 diet basically points to a more humid climate, and C4 points towards more drier climate. So, there was differences. There were differences seen in the diet of the organisms, and this the researchers thought that it could be because there would have been different diet that these animals would have been subjected to. So some may have been in a more C3 diet, some in more C4 diet. But then they thought that what if the animals were grazed around in the area? So what if the animals showed movement in the entire area that was analyzed in southern Africa. And so they went for their third isotope analysis, which was strontium, and in case and they found that the animals displayed very different kinds of activities. So while in case of sheep, they found that some of the sheep were actually taken from one region to another. In case of cattle, they almost lived in the same place throughout their life. And so longer residence was preferred for cattle and not seasonal mobility. And so pastoralism in the late Stone Age was not seen as to be a common practice through strontium analysis. Now, if you take this intact idea, you can also subject other animals through strontium analysis. So in this case, researchers tried to deal with the fossil record of extinct reptiles, or in this case, they even utilized butterflies to understand their migration from one region to another. So if you have that very common idea in mind, and if you can get samples that are less contaminated, you can subject any sort of human species, you can speak human or any sort of animal species to strontium analysis and understand where they might have been going, where they might have come from, if you're able to understand that, or where they would have ended. And it's not just for humans or animals, it's also true for objects. So shell beads, or let's say textiles, so wool, um, ceramics, glass, uh, even in building material, if gypsum and other objects are considered. So you can see that the principle remains the same. The object, human body, animal body, or shell bead, or ceramic, or glass, or whatever it is. The strontium isotope ratio has to be calculated, 87 to 86, and then it has to be compared with the isoscape or the naturally occurring strontium 87 to 86, and to be seen if the material came from there or if the material came from some other place. Um, this is what what the basic principle is, and if you have the basic principle there, you can use it with so many case studies, as researchers have shown. So just to recapitulate here, you have to be very careful about taking in your samples. So you just do not have to think about it. Okay, we found a bone, let's just take it. Okay, we found a tooth sample, or maybe we found a glass from the medieval period. Let's just take it and analyze it. No, you have to think about which climatic condition has been found in, which body part you are taking in, which organism's body part you are taking in, and what would have been the prehistoric climate, not just the climate that you have seen it here, but the contemporary climate that you want to understand. So be very careful about the sample you are taking, then create an isoscape of naturally occurring sample. So you have to talk about geology, you have to talk about lithology, you have to understand the other elements present in the rocks apart from your strontium, if they would have reacted. So basic geochemistry, and then you have to interpret it. You have to compare them. So you need statistics, you need reasoning. And with that being said, you can understand mobility in archaeology. That's the basic idea of strontium isotope analysis. I hope I was clear till now, because now we will be venturing in the critical aspect of strontium isotopes. Till now, I was speaking that it can be used in this case, in that case, it can be used for this sample or that sample. But it's not that simple that you can just understand movement because you have strontium present and you have an isoscape in your hand. So this paper, it's a very recent paper published in 2020. What the researchers did, they took hair sample of an individual living was traveling a lot in the 18 months of their life. So if they have been traveling a lot through different regions, that means they are consuming food from different region, and the strontium ratio that is getting in their body, isotope ratio that is getting in their body, is reflective of the different regions they have traveled. So they thought that maybe we can use a number of isotopes. So in this study, they extracted hydrogen, oxygen, carbon, nitrogen, strontium isotope to understand movement. And turns out that only hydrogen and carbon could actually demonstrate the person's venturing into different regions. Strontium analysis in this case failed to document the person's travel history. Why did this happen? This this is a chart from the same study. So as you can see, the strontium ratios that are there, they are on a fairly similar y-axis. They do show that yes, the person moved to different territories, but the movement was not that. Um, it did not have that span to understand that there was difference of the person moving from one region to other. So this is something that has to be understood that strontium isotopes, although they do differ, there is a minor difference that exists in isotope ratios from one region to another. So almost all strontium isotope ratios of 87 to 86 fall on or around the zero point 0.7 level. So the ratio between the 87 and 86 is zero point 0.7. And in case of older rocks, it can go above 0.710, or in case of younger rocks, it can go below 0.704. So the window of the difference is fairly less, which means, like, if we go back to that very old chart that we had seen, what if the person traveling from one region to another, from Allahabad to Delhi, does not have much of strontium isotope difference? You cannot track mobility in that case because isotope ratios are fairly same in most of the regions. So you have to be very precise and very, very careful when you are talking about movement, because not much difference is seen. As you can see, it's zero point 0.7. Anything is going to be around zero point 0.7. In this case, as you can see, 0.714, 0.713, 712, 711, and 710. And the person has moved through, like, at least they have moved to 3 continents, as you can see. But the ratio does not change a lot. So a very even scope of a minor error can cause huge problems in calibration and would not lead to any results. So this is something that has to be understood, that a lot in a number of regions, a lot of strontium variability, isotope variability is not seen geographically. And this was also pointed by Erickson, who, if you remember, did the first study on strontium isotopes in movement. He said this in the very outset of it, that this problem can exist. Now, another problem that we have to talk about is the landscape that is bearing the natural strontium, which is changing. Yes, agriculture is there, urbanization is there. And in this case study, the researchers actually showed that in Denmark, because of the constant lynching of the soil with leaching of the soil with the lime, the naturally occurring strontium ratio is getting hampered. And if it is getting hampered, it will lead to problems in understanding the isotope ratios. So baseline is the strontium isotope ratio of a given region. That will be different. And if it is different, especially they found this because of difference in the water body that was around on the site and the land that existed, which should have been more or less similar, but it did show difference. And so if that is taking place, it will create problem in getting an accurate strontium baseline for a given region. However, again, in 2021, Fry criticized the last study in saying that the researchers earlier did overestimate addition of lime in soil profile. And even if the leaching of soil has occurred for the last 5 years, it cannot show a number of modifications in the historical context because, as you know, bedrock and the lower soil profiles, they form way back in time. And so causing changes to these older rock profiles is going to be difficult. But then let's bear in mind that this is 2021, we are in 2025, research is still being conducted. So archaeologists are still understanding if changes are occurring to landscape, and it can cause changes in lithological strontium isotopes as well. And so while Fry did criticize the study, in 2 to 3 years, there can be another study saying that no, yes, if there is limestone addition, if there is another addition of pesticides or any other substance to the soil, it will cause problems in strontium isotopes. So bear in mind, this is still a debate going on. Another thing is that when talking about like I like in case of human elements, or in case of archaeological objects, you have the object or the sample in hand. But when you are constructing the isoscape of a region, how do you construct the isoscape of a region? through the rocks that are present there. But researchers have suggested that if you are constructing isoscape of a region, it is better to look for local animals, because the animals who have lived there, they do not show much of trophic level addition or cascading. They reflect the local lithology more as a sample, as a token of understanding the strontium isotope ratios. So usually smaller animals existing in a region, so maybe sheep or cattle, can be used to understand the local strontium isotope of a region to construct the geological isotope. This is again criticized by researchers as an approach because animals move from one region to another, but then there are debates. There are debates, and as people studying archaeology or even understanding about something in a singular instance, in this example about strontium isotopes, we have to be aware of these debates still existing. And therefore, I'll just conclude here by talking about the problems that are there in strontium isotope analysis. Some of them I already mentioned. So there is not much variability in strontium isotope isoscapes, isotope ratios. There are changes that are being made to the modern landscape. We also discussed about weathering earlier. We discussed issues in sampling. Um, we also did point towards this that strontium was a study of exclusion. So it can tell that, yes, the person who has died here did not actually live here, but where did they come from? You can't tell that. Contamination is another major issue. And for that, I would suggest you to go to the last lecture, which was on carbon dating, where we discussed in detail about how much harm contamination can do. Even a trace of contamination can do to any sample. Sample gets restricted, and any sort of isotopic study is expensive. You have to bear this in mind. You have to be very careful that you cannot go on extracting samples and then subjecting them to isotopic laboratory analysis, because first of all, taking samples would damage the artifact itself, would damage the skeleton itself. And if you subject it to laboratory analysis, labs are expensive. They're not everywhere. They're not open everywhere. In a number of archaeological departments, even in renowned universities, there are not isotopic labs. So what is the situation here? And while I said I would conclude here, the conclusion is actually here. I just wanted to mention one last case study and not to make things go overhead, because although there are a number of problems with strontium analysis or isotope analysis, the potential is still immense. And this, I wanted to talk about this case study. It is one of my favorite case studies. Um, so what happens in this case study is that a burial is found. So on the left side, you can see a skeleton that is found. It's of a woman. And on the right side, you can see another burial. This is actually a burial of fetus, of fetus that was present in the woman's body. So the woman would have died pregnant, and the fetus here is the unborn child who would have died in when the woman would have died, and so both of them were buried. And when the researchers found this burial, of course they were able to map the entire life history of the woman. So if you look at the graph on the right, so because the burial was fairly, I would not say intact exactly, but because it had a number of bones present, they were able to understand where the woman what the strontium ratio of the woman would have been there when she was born through the tooth analysis. Then in the later phases of her life, she moved to another place, and so the bones showed a different strontium isotope analysis. And where she died, because of the fetuses, we have the unborn children, their bone analysis was conducted, their isotope analysis was extracted to understand where the woman died. And so you can see that she had a fairly adventurous life. She moved through different regions. And on the left, as you can see, this is these kind of graphs are what we call the violin charts, which are used in strontium studies. Um, so if you see on the right one, it's about that individual burial, and you can see that it's elongated, it's tapering, and it shows movement across the strontium ratios. of that woman throughout her lifespan. And this is something that can also be seen in case of the left chart, where from a number of burials, when a number of burials, like a large sample size, these burials were, the strontium ratios were subjected, the male population was fairly concentrated in the area. The female population, however, showed a variability across the strontium ratio. So if you see the y-axis here, you can see that there is one individual who did travel a lot, and she was not a part of the local strontium baseline. And so this paper suggested that this woman, this particular woman that we are talking about, the burial that we are dealing with, would have come from a very different region and has died in a very different region. It might be an example of exogamy, of marriage from one clan to a different clan. And what the researchers did to understand this further was they utilized the the burial that was present and all the burial goods that were there with the female. So this kind of torque, or what we called as it's an Ossen ring in German, and this Noppen ring or the gold ring, along with these bone pens or needles, were understood. And when the distribution of these artifacts was mapped across Europe, they realized that these two, the nose ring and the torque, were a part of the local culture. So where the woman may have may have died, while the bone ring, the bone needles were found in a more northern profile, in a more northern Europe, which may have been her ancestral home. So the interpretation of this study was that these objects might have been gifted to her as a token of marriage, or when the woman may have come from a different region, she brought her ancestral goods with her, and then she was married to a different clan, and during the time of marriage, she would have received these goods, which were more local, and that is how, with the aid of the isotope as well as with the archaeological objects, by taking both into consideration, the researchers were able to trace her individual biography. This is what the conclusion is and what I just explained. And I end the presentation, the talk here, by saying that reliance on strontium is not the only thing that has to be taken by archaeologists in mind. Your study has to take in more isotopes, and not just more isotopes, not just like strontium, oxygen, carbon, but there are other goods, there are other artifacts that have to be studied as well. So more sources, more diversity of sources as much as possible has to be analyzed to gain a more critical perspective. I said this maybe in the last lecture as well, but I'll say it again. Isotopes are a means of archaeological research. One has to be very cautious of their application, knowing their potentials and limitations, and just not treat them as a magical one solution to every problem. They have their own problems, and that have to be kept in mind. So this is like the selected bibliography. There are many more papers that I studied, especially the case studies. If anyone would want them to be read, I would share them with you guys. So thank you.